Carbon Monitoring System, or the CMS Policy Speaker Series. This series is done on a monthly basis, usually at noon, lunch hour, and the intent of the series is to bring you some of the active science, active applications that are currently going on through policy in the local states or U.S., and really bring them over to Goddard so we can have a better understanding from the outside perspective of how the science is tying in or stitching in with decision support or any kind of policies that are going to be relevant to our research here at Goddard or to NASA as a whole. This policy series is co-sponsored by the Joint Global Carbon Cycle Center. So thank you to George Hurt and to the JCCC for the refreshments and for the snacks. They're generous enough to give that to us on every series. And this actually starts our winter-spring session.
You're no longer muted.
So sorry about that. It's okay. And our speaker to kick off the season is going to be Peter Claggett. Peter works... He's a geographer at the USGS, and he's really going to be speaking to you about the Chesapeake Bay restoration policy decisions and the Chesapeake Bay program. What's interesting for us in terms of CMS is it ties very well into the LIDAR that we have for particular studies. It ties very well into the 3DEP program, so there's significant overlap, and we're hoping to kind of bring some synergies to Goddard. And please feel free to ask Peter questions at the end of his talk. And we are recording this, and we will have people online, so if you are using the chat box, we will read your questions at the very end, and please don't hesitate to raise a hand virtually if you have a question during Peter's talk. So, with no more delay, Peter, thank you so much.
Well, thank you all for coming, and thank you for everybody online who is listening. My name is Peter Claggett, as Vanessa said, with the U.S. Geological Survey. I've been working with the USGS for almost 13 years now. Officially out of the Reston office in the Eastern Geographic Center, but physically in Annapolis, embedded at the Chesapeake Bay Program Office. So with that, with my position there, I can provide some perspective on how managers and decision makers are using remotely sensed data to inform their kind of goals and outcomes, their aspirations. And that's what I'm going to talk about today. So the basic outline is I'm going to go over the Chesapeake Bay restoration effort, kind of give you a 101 version of that. I'm going to talk about types of decisions that are being informed by remotely sensed data and those that potentially could be informed by remotely sensed data, of which there are many. And then talk a little bit about my main role, which is working with managers and trying to kind of translate their goals into something that's measurable. So I'm kind of a middleman in my role between people stating their goals of we want to plant X number of trees and then the data that represents trees from remote sensing information, and how do those two things mesh? Do the data provide and meet the needs of the decision makers? And then briefly touch on some future directions. So for those of you, most of you probably already know this, but the Chesapeake Bay watershed is a big watershed. It's got the biggest land area to water volume ratio of any coastal estuary. It's a ratio of about 14:1. The whole watershed itself is about 64,000 square miles, intersects 6 states. So it's a management challenge because you're dealing with all these different state governments and local governments, about 200 counties in the Chesapeake Bay watershed. But its physical characteristics also mean that what happens on the land really affects the bay. This is a MODIS image the day after Hurricane Ivan in 2004, and you can see the slug of sediment coming down the Susquehanna River. Basically, the bay is a flooded river valley. It's the valley. It's the channel for the Susquehanna that's now been flooded. It's very shallow, which is also why it's productive. So light penetrates, or before it's been polluted, light can penetrate down. You have a lot of submerged aquatic vegetation supporting juvenile fish species and mollusks and other aquatic organisms. But of course, the bay is impaired. The bay itself and 90% of its tidal tributaries are listed by EPA as impaired for nutrients, that's nitrogen and phosphorus, or sediment. And so the Bay Program formed following studies in the 1970s. It formed in the mid-'80s as a cooperative effort between the federal government and the state governments and local governments to do what we can to reduce nutrient and sediment pollution to the bay. Progress has been made over this time period. These are long-term 27-year flow-adjusted trends. And where you see the down triangles pointing down, in purple, those are improving conditions. So in much of the watershed, we see improving conditions for long-term trends in nitrogen, phosphorus, and sediment. But in some areas, like the James River Basin and others, we see worsening conditions. And this is all really heartening that we've made these improvements. It's particularly heartening when you think about the challenge that over this time period, this 27-year time period, the population's increased by 3 million, and yet we've still been able to achieve some reductions in nutrients and sediment and some improvements. These are the population, kind of historic population numbers for the Chesapeake Bay watershed and projected. So we're in 2015 now. There's about 18 million people inhabiting the Chesapeake Bay watershed. That's up from 8 million in 1950. So it's more than doubled since 1950 over a 65-year time span. And the trajectory, the short-term trajectory out to about 2040 is based on local projections. And then we use other information to extrapolate further than that. But there's really no reason for us to think that the long-term trajectory through 2050 is going to be anything different than it's been. So that would mean by 2050 we have another 5 million people inhabiting the bay. So that too presents a real challenge now that we've kind of addressed the low-hanging fruit in terms of nutrient and sediment pollution. How do we reduce it even more, and how do we accommodate 5 more million people while maintaining those reductions? So because the Bay Program has predominantly been a voluntary effort, the governors sign agreements every now and then committing to do stuff. And in 2000, they signed what's called the Chesapeake 2000 Agreement, and they had about 103 different commitments. A little too many, but they had 103 different commitments to do stuff to restore the bay, and a lot of those could either have used or did use some remote sensing information. So one was to do a resource lands assessment. Where are all the farms and the forests and the good habitats across the Chesapeake Bay watershed? Where are they and what is their quality? And for that, we relied on Landsat information. There was another objective to reduce the rate of harmful sprawl. Well, we actually could never really define what harmful sprawl meant from an operational perspective, but that goal to reduce the rate of harmful sprawl is what really kind of sparked the Bay Program into investing in Landsat impervious cover data over multiple years to try to get a handle on how impervious cover has been changing. In 2010, the restoration effort went from voluntary to regulatory. That's where we are now. There's a total maximum daily load limit, a regulated limit on how much pollution can enter the bay. And that limit is below what's going into the bay now. So reduce, get down to that limit, and then maintain that in perpetuity. No matter whether we have 5 million people, 10 million people, or however many million people inhabit the bay watershed, that limit has to be maintained, and it's absolute, regulated by EPA. It's a pollution diet, is another way of expressing it. And the diet is a 25% reduction in nitrogen, 24% reduction in phosphorus, and a 20% reduction in sediment over 2010 levels. Again, we've already addressed a lot of the low-hanging fruits. So this is an immense challenge. And what that means in kind of practical sense is implementation actions, which we call best management practices, things you do, planting creating a wetland, or putting in a stormwater detention basin, things you do to manage pollution, all the stuff that has to be done to meet these regulatory limits has to be done by 2025. So we have 10 more years to do it. Now, the ecosystem is going to take longer. It's not going to respond instantaneously. And in some places, the lag times for groundwater pollution and stuff are on the order of decades. So the ecosystem is going to take a while to respond, and during that response time, the population is still growing. you still have development, you still have land use change, and those nutrient levels are capped. So it makes it a really interesting place to work. And any increase has to be offset. So that's where nutrient trading comes in, hopefully combined with carbon trading and other things. But the focus really has been on kind of water quality trading and how do we, as a means to make restoring the bay basically cheaper. This last year, in June, the governor signed a new agreement to replace Chesapeake 2000. I don't think they call it Chesapeake 2014, but that's basically what it is, Chesapeake 2014. We don't have 101 goals. We have fewer, but a lot of them, in fact, really all of them, on the surface could be informed to some degree by remote sensing information. They actually have a climate resiliency, and which certainly is relevant to this group, but it doesn't mention carbon. There's really no discussion right now of how to integrate carbon reduction, carbon trading into the restoring the bay effort. Individual states are doing a lot, but the bay program has really not advanced very far and probably could use some help along those lines. So some of the goals in Chesapeake 2014 that are using or should use remotely sensed data, I'm going to kind of touch on a few. One is increase the proportion of forest along streams from 60% to 70% throughout the watershed. And I put forest and streams in quotes because this is really where myself and my group, my team come in. What do you mean by forests? How do you map them? What's your baseline for making this decision? What do you even mean by streams? What's a stream? Is it a stream on a 1 to 100,000 scale map? Or is it a stream on a 1 to 24,000 scale map, in which case you have 30% more streams? Or is it a stream, as a biologist would define it in a field, which adds maybe 50% more streams? And of course, as you add those headwater streams, the landscape in the headwater areas is a little different than in the bottomlands, and so you're going to change the proportions of forests and different land cover types along streams. So each of these goals presents a real challenge on kind of how to monitor and how to define it. Expand urban tree canopy by 2,400 acres by the year 2025. Okay, tree canopy, that's a land cover type. Landsat can map that pretty well, but in urban areas you usually need something a little more high resolution, probably more like 1 meter tree canopy. And then how do you define urban? And as urban areas expand, are you going to meet your tree canopy goals? Because now all of a sudden your envelope of which you're encompassing tree canopy has expanded. Obviously, we don't want to do that. We want to meet the goals by planting more trees and having a higher density of trees in existing urban areas. Characterizing the rate of impervious surface change at a scale relevant to county-level decisions. This is really new and probably, I think, one of the most exciting goals they have in there, because we fought for them to characterize change first rather than to set a goal to reduce impervious cover change, because no one knew what the rate of change was. So we said, please just commit to figuring out what it is first, and then a year from now you can set a goal to reduce it. But in particular, they said a scale relevant to county-level decisions. Landsat's great at looking at impervious cover over multiple decades, but Landsat change in impervious cover on an annual basis or a 3-year basis, is that change at a county level that you're likely to see beyond the kind of the error bars in a Landsat land cover data set? That's where we kind of start scratching our heads and saying, well, maybe, maybe not. What level, what's your detection level to be significant, to be meaningful? All those questions have to be worked out. Assessing the vulnerability of healthy watersheds to land use and climate change. Should probably put asterisks around a lot of the words in that statement. But this presents another challenge and a real opportunity for remote sensing information. Achieving and sustaining 185,000 acres of submerged aquatic vegetation. Right now that's being monitored with aerial surveys. Additional instruments have been entertained but never used because of the resolution. Creating or reestablishing 85,000 acres of wetlands. That's another goal, obviously could benefit from remote sensing data. Also a challenge to map wetlands with remote sensing information. So what's interesting to me about a lot of these goals is they're saying do X amount of stuff, increase by this amount, decrease by this amount, but meanwhile, the game board is changing. We live in a dynamic environment, everything's constantly shifting around, and so what managers increasingly, and now they all kind of want to know is, yes, we can track how many trees we plant, but we don't know how many trees are being converted to some other use and not going to be there in the future. So we want an increase in net tree cover, not just accounting for what we do on the ground. And that's a big change, and that's really where I think remote sensing information can step up to the plate. So I briefed the forestry work group. We have a work group for everything. But we have a forestry work group, and I showed them this air photo, and I said, where's the forest? And they were like, right there in the middle. This is right near College Park, UMD on the left. Right there in the middle, and there's a big tract there, and there's a big tract there. But then when you start getting into it, it's like all trees are important. Everything's a forest. Everything's a valuable. How can you really define it? But we have to define it for a lot of our goals. So this is 1 meter tree canopy, resampled to 10 meters. The greener, the more tree, the denser the tree canopy in a pixel. You can go through all kinds of GIS tricks saying where's the big chunks of forest, the big chunks of trees that we might want to call forest. Forest inventory and analysis has a 1 acre minimum mapping unit, so you can kind of go through and say, okay, well, here's all the tree canopy, here's tree canopy over 1 acre, here's tree canopy in red that a 1 acre circle could kind of fit in, it's not as edgy and fragmented. But notice the high level of connectivity with this high resolution data. It actually, for mapping forests, I think Landsat's better because you're not mapping all these kind of neighborhood trees and counting them as forest, which through kind of a Delphi process mostly get weeded out. People say, yeah, that's trees in a neighborhood, that's not forest. But this is just kind of an example of kind of the exercises that we go through with managers and decision makers to try to refine the question in a way that's measurable. Landsat is probably the satellite system we rely on more than any other and have been, and particularly for land cover, land use and land cover information. So a couple years ago, USGS contracted to MDA Federal to produce a consistent land cover data series because we couldn't wait for USGS to do the whole nation, which seems to take forever. But we're getting much better at it, much quicker at it. So we contracted out to get 84, 92, 2001, 2006, all consistent. We've now recently incorporated the 2001 NLCD, but of course classification methods are a little bit different. It wasn't done with everything else we did. We didn't have any more money, and so we can only look at change at the Anderson level 1, like a 5 to 7 class level, throughout these 5 time steps. But these data have been invaluable to us and to the decision makers in the Bay. So just to give you an example, we use classified land cover from Landsat. Green is forest, gray, black is urban, yellow is agricultural or open space. So this is 84 in Montgomery County, Maryland, 1992, 2001, 2006. And what the main change you see in this urban, suburban county is urban development out the 270 corridor. That's kind of the main transition you see in these things. If you actually look at the Anderson level 2 level across the whole Bay watershed, what changes the most over any 2 time steps? It's row crops to pasture and pasture to row crops. By far, that's the dominant change. We don't have a lot of confidence, given how dynamic ag is over a given season, that those transitions are real. And so we kind of throw that out and say, we don't really know. And we go with impervious cover then becomes kind of the dominant change that we see on the landscape. With classified Landsat information, you can get impervious cover. You can quickly quantify that by watershed. What you see in purple is added impervious from row density information. So this is where Landsat, it's too low density for Landsat to fully capture the impervious cover, so we augmented it. And increasingly, we're using additional data sets to augment the remote sensing data to try to get closer to what the managers are trying to track. Impervious cover is great for looking at changes over time in stream flow. As you all are probably well aware, in an urban environment, when it rains, the response of the stream is flashy. The stream levels go up really quickly and then go down really quickly, and that's what you see in red, from a large storm and then a smaller storm. Whereas the blue line represents kind of background natural stream flow response to impervious cover. But having impervious cover through time enables us to look at relationships, and we can look at the flow record through time. This is in the Anacostia watersheds, 4 watersheds in the Anacostia over 70 plus years, to show that flashiness in the stream flow record has steadily increased. And then we can correlate that with what we see in the Landsat record, at least for the last 3 decades, on how changes in impervious have occurred. But again, Landsat, when it captures impervious cover, it doesn't capture everything. So in 2010, when the Bay TMDL was established, we calculated the numbers in red that show the acres of impervious cover and the acres of potentially turf grass, which are in the Bay watershed. And then a couple years later, we said, wait a minute, we're missing some stuff. We started using census, housing density, road density information to try to augment impervious cover, which we thought Landsat was missing, and we came up with almost a 50% increase in impervious cover in the Bay watershed. Managers reacted very strongly to that, not thrilled, and basically the first question was, is that BS? Like, there's no way you just found 50% more impervious cover. So we compared Landsat-derived impervious numbers for 8 counties and our modeled numbers, which showed an increase, for 8 counties that had high-resolution 1-meter impervious cover data or planimetric impervious that was derived from air photos, which you see in black. Our modeled attempt with Landsat plus other data is in dark gray, and the light gray is Landsat by itself. And in all 8 counties around the DC, Baltimore area, we noticed that even with our attempt of adding all these ancillary data, we're still underestimating impervious cover by 5, sometimes 20%. So it presents a real challenge, particularly when you're trying to monitor something over time, and over a couple years, impervious cover may only change a few percentage points, of trying to understand what our baseline should be. So Joe Sexton did some work on his own and then kind of for us under contract to develop annual impervious cover data from Landsat from 1984 to 2010. And that also, we're still trying to kind of explore the utility of that information, but his metrics are more sensitive than just kind of a couple snapshots in time over 20 years. His metrics are more sensitive to picking up impervious cover in the imagery, and he's got it for every year, which has started to change our kind of perspective on how we look at things. Because if you just have a couple time points over multiple decades, you're just drawing straight lines everywhere. And you're saying this is what happened. When you have annual data, or perhaps even seasonal data, which you can only get from a long-term satellite record, then you start to see kind of these abrupt changes and things that correlate better with the economy and some of the drivers of impervious cover change. So that's been really exciting. Another look at satellite. So here's our land cover, Chesapeake Bay land cover data series for 2006. Same color scheme as I described before, where orange is open space and ag. This is 2006 from Landsat. This is 2007, derived from aerial photos with the same color scheme, same classification scheme. And this is for the state of Maryland. You can see between these two images, the Landsat's grainier, but basically looks the same as the air photo derived information. But then when you turn on low-density residential development, that's largely confused in the Landsat imagery for obvious reasons. These are 5 to 20 acre lots as agriculture or something else. And when we look between 1992 and 2006, 19% of all the growth in housing, according to the census, occurred in aerial units, block groups, where we saw no change in land cover, no developed change in land cover. So these are kind of issues where the managers are kind of increasingly becoming concerned, because if we're parameterizing our models based on one heavily weighted towards the remote sensing data, and we're missing, say, suburban sprawl, but we have goals to reduce sprawl, then what are we doing? And so what we've shown over time to the decision makers is that the satellite data is a critical baseline of information that you can get through no other source, but you really need to complement it. So we've tried to complement it with Dasymetric housing maps. So these are 30-meter pixel maps of housing density for 1990, 2000, and 2010 that we derive, similar to Landscan, if you're familiar with that, from census block information for these 3 decades. And that's as far back as we can go with the census block data. So that helps to look over time. We also look at housing density at a census block group level. We can go back to 1940. Of course, this is pre-World War II, at least before the U.S. entered the war. Population centers were around the cities. 1950, 60, 70, 80, 90, 2000, and 2010 gives you a nice long-term record on the spatial patterns of housing development across the whole country. So this, too, is a nice kind of complement to our models and to our understanding of what's happening on the ground. So we've taken Landsat. We still heavily rely on it to parameterize our models, particularly for the patterns of change on the ground. But we drive a lot of our models, particularly our land change model, with exogenous information on population projections and employment projections that the counties produce, because they're already bought into using those data for decisions. They're already assumed we're going to get X number of people in Howard County, where this is, outlined in black, and then we model where residential and commercial growth is going to occur with a stochastic model, again, informed by Landsat for 2015, 2020, 2025, and 2030. And then we model this 101 times across the whole Bay watershed at 30-meter resolution, summarize the results by small watershed or catchment with levels of uncertainty, and we can tell the managers that given a lot of local information, given Landsat over time, this is where we think growth is going to occur. These are the patterns we think are likely or not likely. So that information, because, again, the population's increasing by 5 million out to 2050, managers kind of want to know where they're going to need offsets, where they're going to need to have trades, where is the land changing beneath us that we have to deal with. So another kind of shot comparison of Landsat. This is Arundel Mills Mall between DC and Baltimore. This is 2002. This is actually an air photo. 2010. And the National Land Cover Dataset does a great job picking up this kind of dense urban change on the landscape. And one thing that we really value remote sensing, especially the coarser, 30-meter or 250-meter stuff, is for kind of performing triage across 64,000 square miles. Where are the hot spots of change? If we're going to monitor or sample change on the landscape, what are the places that we absolutely have to include in our sample set? Which is what we did with riparian forest buffers. We used multi-date CCAP, NOAA's land cover product from Landsat, to identify hotspots of change, and then we sampled those with air photos, and we came up with a degree of change over 10 years, 1.8% of the riparian zone, of the forest in the riparian zone in Anne Arundel County changed over this decade with a standard error. So increasingly, decision makers are asking for that. What's the error in your measurement? And if you just say this land cover data set's 85% overall accuracy, that gives them nothing, particularly when the class they care about might be 60% accuracy. we're starting to move towards higher resolution data. And I never actually thought that the program would commit a lot of money to getting high resolution data, but they've recently, as in a few weeks ago, committed to spending over $1 million to get 1 meter land cover for the entire Chesapeake Bay watershed. Actually, they're doing, that 1 million covers everything but Virginia. Virginia has an RFP, which is on the street now, to do the same thing for the whole state of Virginia. And there's kind of an underlying sense that they want to do this repeatedly over time from now into the future. So high-res land cover, what does that get you? Well, this is in Montgomery County. This is a combination, actually, of land use and land cover. This is rural Montgomery County. When you take kind of the residential and impervious cover, you black out part of the landscape. When you look at the trees and the wetlands, you black out or green out another part of the landscape. And everything that you see in the gap area looks like agriculture. I don't know if you can see it from the back, but it's basically kind of open space. When you tally up all those acres in the county, you get something really, really close to the ag census, which the Chesapeake Bay program partners all believe is basically gospel. The ag census is right, it's always right. Well, in this case, this particular county and this particular year combination, it seems like it probably is right. The high-resolution data kind of supports the extent of agricultural land as reported by the census. And this is increasingly for transparency in putting best management practices on the ground to defining the realm of restoration that's needed across 64,000 square miles. This high-res data is becoming more and more valued and will be used. This is the same map attempted with road density, Landsat, housing density from the census, what we could do nationally, and everything in blue is what we would miss. So it's actually called developed in the high res, but missed in the moderate resolution data because they're large lots. And you just, you can't get that from a spectral product. Even a high res product by itself doesn't get that because you have to guesstimate how big the yards are. So finally, in this presentation, I'd like to talk about another kind of high-res direction we're going in, and that's the use of LiDAR elevation data and point cloud data. So this is a map as of last month. It was current on the quality and the extent of LiDAR data in the Bay. And unfortunately, the color schemes shows up poorly here, but the browner of the two browns, the tanner of the two tans, is where we have 1 meter elevation data, quality level 2 LiDAR data. Everything in green is quality level 3. One little area of mauve or purple is quality level 1, and the hash marks are where we have current or planned acquisitions for quality level 2. So what you see is in this area down here is a gap. In the lower left-hand part of the image, we have no LiDAR whatsoever. So USGS's 3DEP program is trying to help the states fill those gaps. USGS is working on others and experimenting with new LiDAR technologies that, like photon counting, that actually may be more, cost efficient for covering a large area at a high point spacing. But this data has really proved useful for a variety of things. One, if you're mapping high-res land cover, how do you tell, buildings from a parking lot? Or how do you tell shrub from trees? The point cloud data from LiDAR are very helpful. They're also really helpful for understanding how water flows off the landscape. So USGS gave a grant to West Virginia University recently. This is a difficult run in Fairfax County. It's a hillshade of the terrain. The tool that they built for us is an automatic stream cross-section tool. It automatically generates a user-defined number of cross-sections across a synthetic stream network derived from LiDAR, and then it extracts the cross-section information. And we use this, and then automatically from the cross-sections, from breaks and slope and other things, calculates channel width, channel depth, or our best attempt, because most LiDAR that exists doesn't penetrate through the water, so we're always underestimating depth, bank angle, floodplain width, and through some of our other scientists' work at USGS, they found that in the field, combinations of these measures and ratios of these measures correlate with bank erosion and sediment deposition in the floodplain. So we can start developing relative sediment budgets for small watersheds based on LiDAR-derived fluvial geomorphic measures. And that's another direction we're headed. So we can extrapolate then from those cross-sections. This is a map of floodplain width for all small catchments in difficult run. And finally, some future directions. As I mentioned, we will be mapping the Bay watershed at 1 meter resolution with an 8 class classification. We hope to do that repeatedly. There are some that have a vision of couple that with LiDAR, some kind of elevation product, and do it, every 3 to 5 years. It's got to get cheaper than it is now, because we don't have $10 million every 5 years. I doubt we'll have that much. But that has a lot of potential. Landsat is the only thing we have consistently going back to the 80s with cloud-free imagery at 30 meter resolution, and now with Landsat 8 continuing on. So mining those data, those archives, developing annual or seasonal products and derivatives to understand change, that is a gold mine of information which right now is not being used that much by decision makers. Developing these hydrologic pathways and a better understanding of hydrologic systems with LiDAR, that's got a lot of potential, something we'll be looking at. Remote sensing of water quality, that's over my 13 years with USGS, that continually every now and then comes up. Why don't you just track water quality in the bay remotely, on a more frequent basis? But something always kicks it out. It's too coarse, it's too uncertain, we're not sure, the satellite just went up, what about the 80s? And so, that's an area where we could use a lot of help. And something I don't have on the list, but kind of wanted to just say is, carbon monitoring also has a lot of potential, and it's something that is really not being discussed that much at the Bay program, but there is kind of an open door for that, because the governors have committed to enhancing the climate resiliency of the Bay. So that's something that I think we could use a lot of help with. Thanks.
For questions, if you guys could just raise your hand, I can get your mics, because we have many people online who would love to hear your questions as well. The mics are not working.
Okay, so you said you guys plan to acquire 1 meter imagery, right? Why can't you use something like NAPE or something? Is it something not suited for what you have, or is there any specific reason to acquire your own data? And the second question is, once you have LiDAR and once you fuse data from different sensors, are you planning to use any kind of non-pixel based classification, or is it all just going to be a pixel based classification to get your land cover mapping?
Okay, thanks. So I probably wasn't clear in my explanation of kind of what we're paying for. We're using the $1 million for everything but Virginia covers the classification only. That doesn't include any, so it's based off of NAPE. So only using existing imagery. But the states and some of the counties have chimed in that we want you to use NAPE plus leaf-off orthophotography, if that exists, plus LiDAR, kind of use all that in an object-oriented segmentation classification scheme, so it's not just purely a pixel-based classification. Right. Sure.
Thank you for your talk, Peter. I wanted to double down on where you ended, which was carbon. As you know, through the NASA carbon monitoring system, we have a couple of projects doing very high resolution carbon mapping and actually modeling. So it could be what we're trying to achieve through that is provide a prototype of the kind of monitoring system that would be needed to get carbon mapping at the resolutions and accuracies that are relevant for carbon trading protocols and ultimately policy decision making. So tying that into what the USGS is doing would be an obvious thing to work towards.
Yeah, thanks, and I totally agree. The mapping effort for all but Virginia they're going to be working with, I think, some of the same people at University of Vermont that are working with you and with Ralph to do some of the biomass carbon mapping. So we'd like to have a closer relationship with your effort.
Just wonder what product levels, what Landsat products are you using to drive your classification process? Are they level 1B or level 2 or?
I should be able to answer that question, but I can't off the top of my head answer that question.
Okay. Just wondering how quantitative you want to get with Landsat products and how it matters to your product generation sort of routines. That was sort of my second question, since.
Well, where I really see the value of Landsat is, again, in this long time horizon, the consistency, the high-res mapping and change detection over time, that introduces a lot of challenges. That Landsat overcomes many of those by, having kind of a consistent footprint, not having to worry as much about shadows and other things. So having, I think, I'd like to see even kind of seasonal products. Basically, products like impervious cover, tree canopy are probably the two main land cover types that we use from Landsat. So, monitoring those on an annual basis at kind of a minimum, I think is one expectation. But other things of, correlating Landsat, we're working with a researcher at West Virginia University, actually with MODIS, where they've used MODIS data to map forest disturbance from gypsy moth, insect defoliation, other things which are just kind of, hopefully short-term, changes in kind of the spectral properties that they can detect with MODIS, and then we can overlay that onto our moderate resolution, our high resolution maps of where the forests are, and say, X% of these forests may be disturbed or were disturbed at, from 2002 to 2004 from gypsy moth, and that actually, there's some work by Keith Eshelman out at the Appalachian Lab from University of Maryland showing how, defoliated forests actually cycle nitrogen differently than forests that are intact. So that information is pertinent to water quality. A lot of forests, if they're leaking nitrogen, we want to know that, and where and when. So increasingly kind of using those types of derivatives from Landsat, I think, is going to be something that's desired.
There's a couple of questions online, and I don't think this mic is working. But the first question is, tracking net changes are an interesting policy option for losses and gains, but this still doesn't get at performance of BMPs. Do you think tracking net changes will correlate with actual design outcomes from BMPs better? And a follow-up question to that is, how well does remote sensing work for tracking SAVs given sediment loads in the bay?
Well, I'll answer the second question first. Yeah, the sediment's a problem. The mushy substrate of the bay, the sediment, which is why there's partly a TMDL. Part of the TMDL is for water clarity, of which it's not great a lot of the time. So that presents a real challenge and might be one of the reasons why the Bay program has never kind of committed to a satellite-derived submerged aquatic vegetation mapping effort. They rely on air photos, flights that are flown at a certain time of year when it's more clear, and then the extent of those SAV beds is hand digitized from the air photos. So sediment's a problem. And if we could kind of get around that, that would be very helpful. For the performance of BMPs, so some BMPs, like planting trees, for example, which I kind of keep going back to, have kind of a direct corollary in remote sensing because you can detect trees. Now, you can't always detect them right after they're planted, but if they survive the deer and everything else, you can see them maybe 5 or 10 years down the road. So one thing we're doing with Urban Tree Canopy is where we have high-resolution data over a community or an urban area. We say, here's your tree canopy for 2010. That means that if you planted any trees before 2000, take them off the books because we should be able to see them and we don't want to double count them. If they're under 10 years old, maybe we can't see them yet, and so, yeah, we'll still count those BMPs. So some of the land cover mapping actually replaces or validates kind of what's there now. And increasingly, if we go to tracking land change at high resolution, every 5 years, then maybe reporting of some BMPs won't be needed. But there is still, and there probably always will be, a need to hold everybody's kind of feet to the fire. If you say you're going to do X number of widgets, install X number of widgets in the ground over this time period, that has to be verified, validated. People have to go out in the field to make sure that the trees are still there or whatever it is, the detention basin isn't clogging up. So there's still a need for that validation. It's not going to be replaced by remote sensing.
The next one is, have you been able to look at spatial patterns of forest cover or urban cover to look at runoff?
Yeah, that's something that is of interest. We've just started doing that. A lot of researchers, people have done that for their dissertations or doing that, as research scientists, that type of thing. We held a workshop with scientists from around the country over the summer on impervious surface connectivity. And, well, it was actually on a lot of things, but the session I was interested in was impervious surface connectivity and how that relates to stream flow, with the idea that if impervious surface is near the stream and it's more tightly packed together, more concentrated, it's going to have a bigger disproportionate impact per unit area on the stream than impervious surface that's dispersed in the watershed. But that's not always true, because the land near the stream is naturally, in many places, it's easily saturated or it's close to saturated, and saturated areas generate runoff. Unsaturated pervious areas do not. And so if you're paving areas that already naturally become saturated very quickly, your delta between the paved condition and the unpaved condition is not very big. Whereas if you're paving recharge areas that can infiltrate a lot of rain over a long time period, your delta is really high. And so you can alter stream flow sometimes by developing kind of the slopes and more the ridges more. That may have, during certain storm events, a bigger effect on flow than developing in the floodplain. Of course, each is bad for its own reason. And there's negative impacts. And so, I'm not saying develop in the floodplain. That's not good. You don't really want to do that. But the management options, how you handle that growth, should be tailored towards the pattern relative to where growth is in the landscape.
The next question is, hello. Okay. No-till adoption and cover cropping are big issues in agriculture currently, related to both carbon sequestration and water quality. Are there efforts to make comprehensive maps of these agriculture management issues across the watershed?
Yes. And that almost sounds like a question from one of my colleagues who's studying that very issue. Dean Hively at USGS over probably the last decade has been looking at that, using a variety of sensors to look at biomass on the fields under different tillage regimes and quantifying that as a way of kind of remote sensing of cover crops. It's validating what farmers put cover crops where, who put cover crops on their land, and the performance of those cover crops. Relating kind of nitrogen uptake to the kind of the health of those cover crops over time. And so Dean's work, and he just happens to be the only person I know who's familiar, who's doing that. I'm sure there's others, but yeah, I think that is a great area for remote sensing. And cover crops are in BMP. That's a great coupling of remote sensing with BMP validation and qualification of how the BMP is functioning.
The last question from online is, given the large carbon stores in estuarine sediment, is a carbon monitoring measurement something remote sensing can address?
Well, I think George could probably speak to this better than me, but yeah, I think carbon monitoring is something ideal for remote sensing to address. But I don't know if is that the exact question?
That was the exact question.
Okay.
Anyone else from the room? Okay.
Thank you. Thank you. I have one question. I saw you detect some area. Do you have a database detect the whole watershed, or establish some database like every 10 days, every month to detect the whole watershed?
No. we don't have any database on a regular. Well, let me just say that we don't avail ourselves. If it exists, we are not availing ourselves of any regular remotely sensed monitoring of the whole watershed.
Okay, thank you.
And let me make a couple reminders. We do have refreshments out here in the side room, supported by the Joint Global Carbon Cycle Center. I believe Peter will be sticking around to avail himself of that food.
And he'd be happy to continue these discussions in that format. Thank you.